Okay, welcome back. So now we have a rendered cloth. The first thing we're going to go through is we're going to actually apply some forces to this cloth, because right now it will just be a static cloth, which is something that we don't really care about. So we're going to make a new function, I will say, under this constructor, like here. That's going to be called void apply gravity. And I can make it inline as well if I want to, which is what I'm going to do, because why not? And I'm going to pass delta time to it so that we have a smoother transition when we apply the gravity. So now, the first thing to figure out is where should we apply the gravity to? So our cloth is going to be static on some of the vertices. Specifically, it's going to be static on the top. So imagine there's a row on our grid that's going to be completely static. So this is going to stay static. Forces will be applied to all the other vertices, and we're going to make sure that after the forces have been applied, and obviously these vertices have been moved, things don't break. So the cloth will be simulated that way. So for this video, so that I keep things a bit short, we're just going to apply some basic forces. So the first one is going to be gravity. You can already imagine how gravity is going to be applied, probably. So we want to apply gravity to every single vertex except that top row. So it would be, well, obviously it's going to be a for statement. And I'll say, why not, size t. And it's going to be y is 1, because we want the first row to be skipped. And here, basically, we're going to have our grid resolution that we made or chose, and just y++. For the one under it, we have to go through all of the vertices on each row. So we have to say size t, x is 0, because we want to apply it to every single one of each of these rows. X smaller than grid res, and x++. Good. So now what we have to do is get the current position. So here we're storing a few things. We have vertices, indices, all we need for rendering. But ideally, I would want to also save the previous position of the vertices. So I'm storing the vertices now, so I'm just storing the current position of the vertices. I'm just going to make another one here that's going to be, I'm going to call it prev vertices. So this is the previous position of the vertices. So I can go back to my apply gravity function, and I can start, well, first of all, to apply the gravity, I need to get the current position so I know where I am. So you can kind of figure out exactly what we're doing this, right? We're applying gravity, which is a force. We can't just apply the force to the position. We have to apply it to basically so that we actually add some acceleration. And because we're not going to be using acceleration, because acceleration is real bad to be used in physics, we're going to be using velocity. And we're not going to be actually explicitly using velocity. We're going to be using it through position. So we're going to track the previous position, the current position, and that way the difference can give us the velocity in each frame. So we're not going to be explicitly using velocity in this simulation, which is completely fine. So we have a GLM vec3 here, which is going to be, I'll say, our current position, just to make things a bit more clean. So vertices, vertices, obviously it's going to be x times our grid res, or x plus y times our grid res, to give us exactly the value in the area that we want, dot pos, which is our position. And we have the position of the first of the vertex. Now we also want the previous position, so we'll do exactly the same thing here. So I'll say prev pos, prev vertices, same exact thing here for the element, for the indexing, and pause. So now we have our positions. So from these two values, we can determine the actual velocity of that specific vertex without actually storing the velocity. So now what we have to do is we have to actually apply that force. So we're going to go vertices. So that force will be applied to, obviously, the vertex itself, so to its position, because we're not storing any, acceleration. We're not storing any velocity. So here we have grid res again. So we're getting our current vertex, and we're saying position, and we're going to say plus equals, this is the application of the gravity. We need the current velocity, which is going to be current pos minus prev pos, right? Current position minus the previous position, plus gravity, which is going to be a value that we're going to set on top, times delta time. So we basically apply this force. Okay, so before we do anything underneath, let's go up here and basically just give a value to our gravity function, or to our gravity. So what I'm going to do is, obviously you saw how that looked like, right? Like this is GLM vec3, so we need a GLM vec3 for gravity. I'm going to go in here and define gravity. So I'm going to say gravity. I'll say 0.003F, which is a good value for it. And now I'm going to actually go up here and say const, because remember we need a GLM vec3 for the gravity. Gravity. And this is the value that we're actually using. So it's going to be 0.0F on the x-axis, obviously. Gravity here on the y-axis. And on the z-axis, it's just going to be 0.0F. So now this should be, minus, obviously. Oops. So minus gravity. So this now is the gravity that we're applying down to our gravity function. So that's done. And now we can move on to, well, there's one more step here, right? After we're done with these loops and we apply gravity to all of these pixels, not pixels, vertices, we need to also update the previous positions, because these are the current positions. They have now been updated. We need to update these as well. So that's quite important. So we have the current position here that we stored. So that hasn't changed. So we can use that to update this this vertex's current position. So we can again say x plus y times grid res dot pos, and just say current position. So now it doesn't like it. And I put it in the wrong spot, so let's just put it, where was it? And let's put it here. Great. So now we're applying gravity to our current vertex that we're processing, and then also storing the previous position so that we can actually measure the velocity, like between current position and prev pos. Awesome. I also don't really like prev vertices. Sorry, but I'm going to actually change it to pre-vertices, because prev vertices, it looks a little bit weird. Just a preference. Okay, good. So now we're applying gravity. The other force that we can have in general, it can either be wind. I mean, we can have collisions, but we're not going to do collisions for this tutorial. But we can have wind, which is almost like a random force that's been applied, which we're going to do eventually, but not now. And we can have drag. And drag is a little bit more interesting here, because if we don't apply drag, basically gravity will keep being applied and there will be no drag, so everything will just keep moving because there is no friction. So we're going to make a function called inline void. No, I'm not making it inline. Void add drag. And again, I'm going to pass So I'm going to pass two things here. So I want to be able to control how much drag I'm applying. So basically I want to force just a value that's going to basically scale how much of this drag has been used, which is already part of the UI that you have from ImGUI. So I'm going to call this float drag. And here I'm going to also pass delta time. Good. So again, remember that we're not actually applying any forces to the top row. So again, we're going to say size t y is 1. Grid res y++, because we're skipping the first one. And then we're saying for size t, x 0, and then x smaller than grid res, x++. Awesome. So now we want to apply the drag. And we're going to use this, again, we're applying drag to velocity, which we don't have. So we can just copy these two lines to get our velocity, or the information that we need for the velocity. So we start with this, and then we need to calculate the direction of the drag. So we can say constant glm vec3, let's say drag direction. And the direction of the drag is going to be the opposite direction to the velocity. Now you can normalize this to actually have the direction, or not normalize it. You can test the results. They're similar-ish. So just go with your preference, really. So again, remember before our velocity was current pos minus prev pos. Now we went to reverse it. So we just reverse the order of the operation here. Oops. Prev pos. So prev pos minus current pos. So now that we have the direction, we can actually apply that. So we can say, again, vertices, x plus y times grid res dot position is going to be our current velocity. So current pos, oh God. Our current pos minus prev pos plus our drag direction, so plus the force, times drag, which is our scale value of the force, times delta time. Awesome. So now we have actually updated position based on this force. And remember, again, we do need to store the previous position so that we keep these updated. So we can again say x plus y times grid res dot pos equals our prev position. Current position. Awesome. So these two, this one applies gravity, this one applies drag. And we kind of need both for simulation. Because obviously we don't apply gravity, nothing happens, it just stays still. We don't apply drag, it will just keep going very unrealistically. Wind will be done at some point. It's very similar to drag, but it's just the value or the direction is actually a normalized vector that is random, right? So we have 3 values that are random. We're not going to do that though yet. So what we can do now is kind of apply these. Obviously, we do not simulate this yet, so we don't solve constraints yet. So we're not actually able to keep our cloth together, but we can kind of see whether it's actually working. So right now, all we do, if we go back to our main CPP, is we render the cloth. But we want to do more. So let's make a function above render called void, let's say simulate. So here we'll put all the things that we need to actually run the simulation before we render the cloth. So I'm going to say bool first, wind flag. So I'm going to pass everything when we apply wind. We're not going to use that yet. Then we want a scale value for the wind, Then we want the bool flag for the drag, so we can control whether we're actually applying drag or not. And again, a float for the drag, because remember we have a scale value. And we're going to pass our model matrix here as well. Oops. No, we don't really need that. We would need it for collisions, but for the purposes of this, let's not do it yet. And our delta time. So all of these will come from our main function and basically update all of the vertices before we actually render it, the cloth. So a simulation in general runs in steps. And because we're doing a verlet simulation, we're going to start with some specific verlet steps. So I'm going to say 4. So these are the simulation steps. So int step. So these happen every single frame. Step smaller than, I don't know, verlet steps. So we're going to make another constant that looks like this. Step plus plus. And here we're going to put everything that we need. Let's first define verlet steps up here. So define verlet steps, and let's say, well, we're going to be changing the value a bit, but let's say 3, because that's nice. And let's scroll back down to our simulate function. And what we want to do now is we want to update. So a few things. We want to obviously use our gravity. It's the first thing we're going to do. So we're going to apply gravity to all vertices. So all I'm saying is apply gravity. And obviously I need to pass my dt, and that's it. The next step, so that happens either way. We will always apply gravity. We really don't have a reason to control this flag or this function or whether it happens or not per frame. So we're going to apply gravity every frame. Then we have a drag flag. So I'm going to say, well, if we are applying drag, then we just add drag. Good. And again, we're passing our drag, scale value, and our dt. We're doing exactly the same thing for wind, although wind won't happen. So I'm just going to skip it. So I'm just going to say to do add wind when implemented. Because why not? So this is going to be the application of the forces. We're not going to be doing collisions here. So these are going to be the applied forces. The next step is, underneath here would be to actually constrain the vertices so that they actually don't jump around. So here I'm going to also say to do constrain, or I'm going to say apply constraints. Oh, wow. Okay. So this is all we need right now. We update the vertices based on gravity and drag. So the next step in our before rendering is to actually pass these new vertices to our GPU. Because remember that our vertex array on the constructor will actually have our initial vertices, but when we're updating them here in gravity and drag, these are not passed to the GPU yet. So we do need a function that just updates the vertices. And that's going to be a very simple function. And I'm going to put it here. Why not? So void update vertices. And I'm going to pass nothing. So here all we have to do is bind the buffer. Again, if you don't care about graphics APIs, doesn't really matter. So we want our RA buffer here, our VBO. And all we want to do is say GL buffer data to pass the data. And again, RA buffer that we just bound or bind it. Vertices, size, time, time. So it's exactly the same line as the one in the constructor, right? So no need to explain it. Our data, so our pointer to our vector, of vertices and GL dynamic draw, because why not? So this now will update our vertices. So let's go back to our main CPP. Before we render the cloth, we actually want to kind of simulate. Well, I'm not going to say much about it, but before we actually do this cloth.render, well, we have to say cloth.simulate. So we're going to pass our wind flag. So just copy these values because they're already on the GUI. You don't really need to care about where these are and what these are. So this is going to be sim wind, sim drag, sim wind amount, sim drag. So these are the flags. And now the actual value. So sim drag amount. And I'm going to go under it. And I'm going to say static cast float. And we have a timer, remember. We're going to get our data from that timer. And say delta time. The reason is this is a double. So that's why I'm static casting it to float. And here I'm going to say times settings dot sim speed, which basically what it does is it allows me to manipulate delta time a little bit before passing it to the simulate function, so I can slow down or speed up the simulation. So now that we've made our prev vertices, we can go back to the constructor here. And we also need to pass these initial values here. So obviously what that means is we calculate our vertices here, and you can see them. And we also need to pass those to our prev vertices as well. So we have to say prev, or pre-vertices, equals standard vector. So we need to, remember, copy this. So we need to do this properly. Symbol vertex and vertices. So this will create a new vector that's a copy of this vector. So I noticed a small issue here. For some reason, I said steps larger than verlet steps. Should be smaller, obviously. So that should be fine. And it was actually a warning here that actually told me, but it's okay. So this should go away now, but okay. So we're now simulating and we're rendering. And obviously yet, I'm not actually updating my vertices, so we'll see that nothing happens, but we might as well just run it, build and run, to see that everything kind of works and builds actually, not works. So our cloth is still here, which is good news. And it seems to be working fine. Obviously the animation is not playing, but we're not actually using whether it's playing or not. So, okay, the simulate probably works. So before we do this, we're going to render every single frame, but we want to actually control when we're simulating. So I can pause it and see if everything is fine. So I'm going to say settings.run sim. And I'm going to put this. Oh, wow. So I'm going to put simulate in there. And now I'm also going to put cloth dot update vertices in there as well. So now if we have the setting to run the simulation, we're going to simulate, so update the vertices and then pass the vertices to update them on the GPU and then render. We render every frame, by the way. Okay, we have our cloth. It's still here, which is good. It's good first step. If I hit P on my keyboard, you can see that it starts falling. And you can see exactly what's going on. All of these are falling at exactly the same rate, which makes sense. But these vertices here on this row are remaining still. So they remain fixed, which is exactly what we wanted. Obviously, this is not going to constrain itself. So if I hit P, it's still going to be going down. And if I go down here now and I see this, I can also apply drag and just add quite a bit of drag if I wanted to, which cause all sorts of weird effects because right now we're not fixing anything. So the point is we're applying the main forces. What we do need to do now is to actually make sure that the vertices remain almost the same length between each other, so the same distance between each other, and that's exactly what our constraint solver is going to be doing, which we're going to explore in the next video. I hope you enjoyed it, and see you in the next one.